Today we will be talking basically about multiple linear regression. Okay. When we began to talk about regression, we talked about simple linear regression. Now, in a simple linear regression, we have one dependent variable and we have one independent variable. For example, the amount of money that a person spends on clothing is a dependent variable that depends on their income, the independent variable. And so the point we're making here is that the amount of money spent on clothing depends only on income, which may not be true, because there are other variables that affect how much money people spend on their clothing. Essentially, when you measure just expenditure on clothing against income, what you're really measuring is the marginal propensity to spend on clothing out of income. And so for each dollar increase or change in income, how many additional cents does somebody spend on clothing? How many cents less do they spend on clothing? That's essentially what you're measuring. But when you come to think about it, the amount of money that is spent on clothing could depend on other things, which, for example, definitely it would depend on income. Somebody who doesn't have money does not spend. But it could also depend on the price of other goods, okay? Other things that somebody might desire. So if they say the price of meat that the person wants to eat, changes, or how much they spend on food, then they may not spend so much additional money on clothing. Now, so for this purpose, I'm going to pull up a PowerPoint slide and look at some of the examples that we have. And we use that to illustrate, because I'm going to look at the homework assignment that I gave, and it's pretty straightforward. So that even when we come back next week, I'm going to be sure to grade those homework assignments for next week, Tuesday, on multiple regression especially, and point out where the errors lie. Everybody will have an opportunity to go and redo the assignment if they feel like doing so. Okay, so I'm going to pull up, I'm going to share a PowerPoint slide. All right, so you see, are you seeing my screen?
Yes.
Okay, so this is an example of multiple regression. Like we said, there is one independent variable. The dependent variable is y. And then there are several independent variables. We'll call them x1, x2, x3, up to xk. And they could be as many independent variables as possible. Okay, so now for an illustration or an example, let us say the wages that somebody earns, the kind of salary they are paid, depend on the amount of education, the years of experience, gender, and tenure on the job. Okay, somebody who has stayed longer on the job is expected to earn more money than somebody who has stayed less. And the years of education also could be a factor, in the sense that somebody who has, more degrees is likely to be put in a position where they're going to make more money. Okay, so then years of experience. If somebody has a lot of experience elsewhere, they're going to be offered more money than somebody who has no experience. All right, so this is an example of multiple regression, and I'm going to try to illustrate it further. Okay. Let's see. All right. And so for this particular example, I'm going to say that y is equal to, of course, the constant a plus 1 times x1 plus 2 times x2 plus v3 times x3, and you can just go on to bk times xk. Okay, so a is the constant value. Okay, if all the x's are 0, then b1, for example, is how much does x1 affect y? Okay, holding the other variables constant. And b2 is how much does x2 affect y, holding the other variables constant, and so forth and so on until you go to the last variable. So that's essentially the way you specify the model. Okay. All right. So I'm going to use a simple example to illustrate that. And once we have this example, we illustrate it, and then we can calculate, we can use the values that we get to predict and to calculate the value of a dependent variable given different values of the independent variables. So in this particular example, we're going to look at housing. Okay, the dependent variable is price, and the independent variables are size, distance from the city, and number of bedrooms. And so let's see if we can illustrate that. Okay, and so price is the dependent variable, y, is equal to a, the constant, plus b1 times size. So I'm going to reduce that. Let's play with that. Size plus b2 times distance plus b3 times the number of bedrooms. Okay, so that is essentially what we have. And so b1 says if the size of the bedroom increases by 1 square foot, how much would the price of the house change? That is the basic question we are asking here. If the distance from the city changes by 1 mile, how much will that affect price? We measure that by the size of B2, okay? And at the end, we have to account for error. So this is the model equation, and we're going to estimate. Now, I'm not taking you through the trouble of running the SPSS programs because we don't have that facility, but over time we're going to have to do it, but not in this class, not this semester. So now when we run the program, we obtain the parameters, and these are the parameters that we obtain, okay? And so what I want you to do is to be able to interpret these parameters, to interpret these results, okay? I need for you to interpret the results. As we said, the dependent variable is price, okay, in thousands of dollars. Therefore, Y is equal to 130,939 plus 39.106 times size. So if the size of the house increases by 1 square foot, then the price of the house will increase by $39. Okay. If the distance from the city increases by 1 mile, then the price of the house will decrease by 2,606. As you can see, the coefficient of distance is negative, okay? If the number of bedrooms increase by 1 more bedroom, then the price of the house will change by 10,874. As you can see that the number of bedrooms really has a big impact on the price of a house. Okay, again, it depends on the way people judge what they want in a house. Okay, you want a big house with just 2 bedrooms, or they want a smaller house with 4 bedrooms. As you can see here, the buyers in this particular neighborhood that we sampled are more concerned about the number of bedrooms rather than the size of the house. Okay. Now, when we run our regression, we obtain also the other parameters that we get, which is an arrow square, which is to say, in this particular instance, you can see that 33.2% of the changes in the price of a house are explained by the changes in those independent variables. Okay, so we still have quite a bit to explain, but for now, let's just interpret the R square for what it says. All right, so now we want to use the information to calculate the price of a house. Okay, suppose we have a house that is 1,600 square feet, 20 miles from the city center, and it has 3 bedrooms. What will be the price of the house? Okay, the price of the house would be, okay, 130,939 plus 39.106 times 1,600 square foot minus 2,606 times the distance from the city, okay? This is, we said the city is 20 miles, and so 2,606 times 20 plus 10,874 times 3, given that we're looking at 3 bedrooms. When you do all of that calculation, what do you find? You find out that a house with these parameters, with these characteristics, will be selling for approximately 173,980, give or take. Remember, that's error in your calculation. So that is very simple way of looking at multiple regression. All right, so now that we have estimated the parameters, the slopes of the various independent variables. We also need to be mindful that our estimates may not be meaningful, in the sense that we can argue that neither size nor distance nor the number of bedrooms has any effect on the price of a house. Maybe there are other variables that have an effect on the price of the house, but not these variables that we have here, okay? So we go through a test of hypothesis, and this is a formality, as you know. Okay. So to go through a test of hypothesis, you have to set up your null and alternate hypothesis. And here, the null hypothesis is designed to test each individual independent variable separately. Okay, you test each of them separately. All right. So this is why we say beta sub I. Okay, I meaning the ith independent variable, and so it could be beta sub 1, which is the slope of one of the variables, the first variable, which we call size, and it could be beta of the second independent variable, or the third independent variable, or the fourth, and so forth and so on. So you're testing the hypothesis for each independent variable separately. The null hypothesis is that the independent variable has no significant effect. That is the null hypothesis, which is to say that the particular independent variable you are testing has a slope equal to 0. There's no effect, no significant effect. The alternate hypothesis is that the independent variable you are testing does have a significant effect. Okay? All right. So we select the significance level. 0.05 could be different, could be 0.025. Okay. Well, this is for 0.025, and Z star is 1.96. Okay. The Z star for 0.025 is 1.96. So we proceed. Okay. And so we find that from our result, let me pull it up here. Okay. I'm going to see if copying it is going to make a difference. Okay. So as you can see here, we look at size of house in square feet. All right. Does size of house in square feet have a significant effect? We use our usual rule. Okay. Okay. We calculate Z, and from this result, we see that Z is 2.34. Okay. Z is 2.34, and our Z star is 1.96. And the decision rule, which we all know, is that if Z is greater than Z star, actually if Z is greater than or equal to Z star, we reject the null hypothesis, and I'm going to Z is greater than or equal to Z star. Okay. If Z is greater than or equal to Z star, we reject the null hypothesis that B is 0. Okay. We are rejecting the null hypothesis that size has no significant effect. That is what we're saying. Okay. Therefore, the independent variable size of the house has significant effect. Okay. And so we can include that in our calculations. Okay. So here's another example. This is the housing problem, not wages. House price problem, because we're looking here at size, and so you can see the Z calculations below. This is why we put those in brackets. Those are the Z calculations. So you have to use them, and what I want you to be able to do is to read off those Z calculations in brackets below and use them to test the hypothesis. Now, the next thing that we need to talk about is something called dummy variables, okay? Dummy variables. And I need for you to understand what dummy variables are, okay? We're now looking at a different problem, okay? We're looking at the wages problem, okay? So we're asking here, the salary is dependent on what? The salary is dependent on education, years of work experience, gender, and unionization, okay? Now, you don't measure gender the way you measure years of experience. I mean, a variable like gender has only two possible values, one for female, zero for male, or vice versa, okay? And a variable like belonging to a union, you can only belong to union, you don't belong to union. And so since there's only a dichotomy of values, one or zero, as either it is or it is not. We call such variables dummy variables in regression analysis. We call them dummy variables. And so we plug them in, okay? Now, if the value of the dummy variable is positive, that means that the variable has a positive impact on the dependent variable. If the value of the dummy variable is negative, then we say that that particular variable has a negative impact on the dependent variable. And we simply go through a test of hypothesis the way we did with the house price problem to measure the impact. Okay, so here we have an example. Are you seeing the screen better now?
Yeah.
Okay. So again, our null hypothesis is that these variables have no effect, and you can see all the Z calculations are in brackets, okay? And we're testing at 0.005 level of significance, and so our critical Z value is 2.58, all right? And the decision rule applies, okay? The null hypothesis is that education has no effect. Well, when you compare 5.874 to the critical of 2.58, of course, you reject the null hypothesis that education has no effect. But what the model says here is that, of course, if you have no education, your income is going to be practically zero. But for each additional year of education, your income will increase by 3,300. And for each year of experience, your income will increase by 447. But being female is a disadvantage. You can see that being female penalizes the individual by a salary reduction of about $11,000. Now, how about belonging to union? You can see that prima facie, it says that belonging to union has a negative impact. But you also see that if you compare the absolute value of the Z value of 1.405, then you are not able to reject the null hypothesis that unionization has no impact. Whether you belong to union or you don't belong to union does not affect the person adversely, because you can see here using the absolute value 1.405 and comparing it to 2.58, that the unionization does not really adversely affect a person's income. Okay, so that's all we have for today. Do you have any questions? And did you complete the homework assignment for that week?
I completed. I don't have any questions.
Okay, all right. So next week we're going to go through index numbers, because I want to go through index numbers systematically before I begin to do the examples.
Okay.
All right?
Yeah.
Okay. So I'll see you all next week then.
Okay. Have a good evening.
And you too.
Thank you. Bye.